So it is better now. Faith, let others join. So I will give about 15 minutes grace. Can you people still hear me? So I'm waiting for more people to join. Can you people still hear me? Can you see what is showing? Can you see what is showing? Is it better now? Watch it. Expand it now. Let me even join and see. Let me use another this thing and join and see what the complaint is all about. But I don't understand what you can. Hmm? Can you hear me? Okay, since we are having issue of clarity here, and this is the highest this thing can go. I don't know how I can share it better, but I think I should proceed. We are just 25 minutes late. Last week we solved this question for the series magnetic circuit of figure 11.29 here. Can you see my mouse? Last we saw this question for the series magnetic circuit of figure 11.5. Here, can you see my mouse? My mouse. Okay. So we solved this question last week, and we were able to. Hold on, I think I used my hand to. We were able to get us. Hmm? So the question is, let's repeat it again. If you can still hear me, let's repeat it. Series magnetic circuit of figure 11, 21, 29. Find the value of current magnetic flux of 4 times 10 raised to power minus. Determine the permeability and the relative permeability for the magnetic condition. So we have the magnetic circuit, which is represented with this symbol. This symbol here, the symbol of A. This is, we are still learning this process. Just bear with me. Let's move down to the solution. So we have our flux density, which is what we are meant to calculate. The flux density is phi over area. And we have our area to be 2 times 10 raised to power minus 3. I think is here, is written on this, is written here. This is what we are analyzing. Are you seeing figure 11.9? We indicate. So since we have our area, we have the number of turn and the length of this magnetic circuit. The length of the magnetic circuit is 0.16 meter. The number of turn is 400 tons, and the area is 2 times 10 raised to power minus 3 meters square. Our magnetic density is equals to phi over area. This was the formula I gave you last week. And phi here is 4 times 10 raised to power minus 4, and area is 2 times 10 raised to power minus 3. And when you divide them, you will have it to be 2 times 10 raised to power minus 1, which is 0.2 Tesla, or you say is 0.2 Weber per meter square. So for this B that we are looking for in table 11.2, you feel it to be 0.2 Tesla. Then another one is the magnetizing force. The magnetizing force, which is H. And H, because it's a cast iron steel, H is equals to 170 over M. So applying the Ampere circuital law, we yield that Ni is equals to H of L. And remember that Ni is equals to force. Ni is equals to force from our previous formula. Ni is equals to force. You can go to the last formulas I gave you. And that force is equals to, if we want to calculate the magnetizing moment, we say that is force per what area. So we now have that Ni, which is force, over Ni, which is force, is equals to HL. Let's go back to the formula of that last week so that you see it clearly. So this is the formula we discussed last week. This is force, which is Ni, and magnetizing force is equals to force per length. You can see it very clearly here. Why I'm just trying to drag is that I can't even get feedback from you. So it's me at all. If I can hear from you that what we are doing, we are proceeding, there would have been a better something. The transmission would have been seamless. But notwithstanding, let's still proceed. So we have this as the magnetizing force, where H is equals to Ni. Remember that last week I told you that force is equals to number of turns times current. And the magnetizing force is number of turns times current all over number of length. So let's go back. So we have our length to be 0.16 meter and number of tons to be 400 tons. So applying it to this circuit, we have that 170, which is the magnetizing force for cast steel, times by length over 400 tons, will give us 68 milliampere. 68 milliampere. I will still copy this thing and send to you on the platform so that you go through it. Then the permeability of the material, which is B over magnetizing force. B over magnetizing force. So the magnetizing force forecast here is 170, while the magnetic density is 0.2 Tesla. So when you calculate them, you have 1.76 times 10 raised to power minus 3 Weber over the permeability of free space, which is 4 pi times 10 raised to power minus 7. And when you do that, we have 935.8, 935.8. And this material should be ferromagnetic material, because for ferromagnetic material, the relative permeability is above 100. So let's do for this other one. Hilary said that we can't see it. So the next thing we are going to do today, we've solved one question, is to do transformer. And when we talk about transformer uses the principle of electromagnetic induction. And what we know as a transformer is something that can improve the output of an input, something that can make an output to increase or decrease. And what transformer does is that they increase voltage or current. Transformer increases voltage or decreases voltage. Or you can say that transformer can increase voltage or current. But transformer cannot transform power. Transformer cannot transform power. And why do we say that? We are going to do some of the calculations and you understand why a transformer cannot transform power. People should hold on. Let me get some things out. Where's my workbench? So in this transformer, for easy explanation, I'm going to run a simulation with the system and show you what I mean. That a transformer cannot transform power, but it can change the voltage level or the current level of the input. And the principle of this transformer is that it uses magnetic flux, what we've been discussing before. The change in magnetic flux of the input, which is the primary section, and that of the secondary section determine what the voltage level can be. For a transformer, we have coils of wire, like when you turn a wire into tons of wire. When you roll a wire, maybe you can use your biro, you roll a wire, bring them together. There is a magnetic flux existing between that ton of wire. I've explained this thing using the Lenz's law. Okay, Mbafit, transformer increases both voltage and current, and it equally decreases voltage and current. But the way it does it is what we are going to see. I will share this screen for you. Just hold on. This will should hold on. I'm trying to run simulation so that we look at it.